So it's a great pleasure to have Eric Emsellem here today. Eric got his PhD at Crown in Lyon before starting his journey around the world. So I think he has been to Leiden. He was a fellow at ISO in Garching and then back to Lyon. And well, now he's the head of the project science department at ISO in Garching. So he's leading and mentoring project scientists, supporting the main facilities of ISO, so I think ALMA, VLT, the ELT as well. Yeah. And he's also the initiator and the co-lead of the ISO Open Science Initiative. And I think maybe if you are interested in that, you can talk to him later. He will be here only today at the guest office in the third floor. So apart from his experience in designing and building and exploiting state-of-the-art instruments and facilities, Eric is also an expert on dynamics. So I think he will talk about this today.
Yes.
Thank you.
Thank you so much, Anita, and thanks to Fabio and Anita for the invitation. It's a pleasure to be back in Bologna after so many years. The weather was not with me, but I hope next time I come, you bring the, you call the sun for me. So today I'm going to talk about basically two things which are interconnected. I'm basically going to talk about bars, galactic bars. So this structure, this beautiful structure you see in galaxies at low redshift, and now people start seeing them at high redshift, or maybe they see them at high redshift. And I don't think you will understand the subtitle here, especially if you're not American. I'm not American, I'm French, but I may explain this by the end. If I forget it, you can ask me what it is about, but it's about the prohibition rules in early 20th century in the US, and there's a reason, of course. I mean, the most important thing is collaborators, because I'm presenting, I'm doing the shiny thing, but of course there are a lot of people who worked, including two people who are doing expert simulations, Florent Renaud and Oscar Agertz. Florent is now in Strasbourg and Oscar in Sweden. But also I want to emphasize, and you will see his picture, Pierre Verfilken, who is now a successful PhD candidate, just defended earlier this year, who did, I would say, something like 80 to 90% of the work that I'm going to present in the second part of the talk. And so the first part of the talk will be more about general statements, and I hope it's not too boring for you, but I'm going to try to provoke, at least if there are any people doing cosmological simulations here. I'm not, so it's easy for me to criticize, and this is why, if there's a discussion, it would be nice to talk about this. And so what I would like to talk to you about is galactic evolution in general, looking at low redshift objects. And I think I will start with two slides, two statements that for me is the basis for the work I'm going to present. The first statement is that if you look at the life of the universe and the galaxies as they are today, most of the stars you will observe are actually formed in disks. It's very hard to see if you have a galaxy with, let's say, a spheroid and a disk or whatever structure, even an elliptical, a galaxy which is a bit more fluffy, to say that the stars are actually formed in this, above the disk or in the spheroid. They mostly form in disk structure. It doesn't mean the disk will survive the 13.5 gigayears, but at the end of the day, where they're formed is usually in a disk. And at different levels, at high redshift, there's a lot of gas and turbulence. At low redshift, it's a bit more quiet. But I think this is the statement that I would like to emphasize here. And this is just a standard Kennicutt-Schmidt law in a diagram where you have, for many, many galaxies in the nearby universe, the star formation rate in some solar masses per year in log, and then the stellar mass of the object. And you see, I mean, galaxies are a bit messy here, but people define what we call the main sequence, just fitting this line here, and sometimes it goes up, actually. There is a modern version where there's a broken power law. Whether you believe if it's relevant or not, this is not the question here. And you have here, I just I put the LMC, the Milky Way, and the Andromeda galaxy in different places, and some people disagree about this. Whether the Milky Way, for example, is a main sequence star-forming galaxy or not. It's not the point of my talk, but what I wanted to present you with is kind of a global picture with two very simple metrics used to look at the properties of galaxies. And of course, if you are well above this, you have the starburst galaxies. And here you have the dwarfs, the smaller one, the bigger ones here. But it looks like if you look at really bigger samples, that there is indeed a reach here, a set of galaxies where as you go for higher mass, the star formation rate goes up, the power low. Galaxies here are often called the Green Valley galaxies, the ones that are a bit star forming, but not really as much as those ones. And then here you have the what people call the passive galaxies. Usually they are called early types. But again, the statement in this slide, the most important is that most of the stars you see today, wherever they are in this diagram, have formed in disks. So it tells you that disks must be important to study at high redshift and low redshift and try to understand galactic evolution. And the other thing I want to do here in the second slide is to use beautiful images from the JWST, so the James Webb telescope, of a number of nearby galaxies, disks, galaxies of different masses, low mass, dwarfs, and more massive ones, to show you the diversity of structure you see. So what you see here is actually a combination of different bands. In blue, you see more or less the stars in those, so the skeleton of the galaxy, while in reddish, you see more dust and the ISM, the interstellar medium. So this is just the emission in the infrared that comes out. And you see this beautiful set of structures, sometimes very messy, sometimes very ordered in those disk galaxies. And this is a good representative sample, let's say, of what's happening at low redshift in disks. And as you can see, the number of structure, or the variety of structure is high. And to understand this, you need to do dynamics, but you also need to do evolution to understand how the disks end up being like this. And whether this is important to understand actually their entire history. So what would be nice is now that we have a way to start at very high redshift and go down and have some kind of reference path of how galaxies are evolving, especially the disks one, because this is where you will form the new stars. Even if after they are messed up with some interaction or merging, they will form there. And so understanding the structure as equals 0, where we have the highest resolution, the highest numbers, a number of data pieces of information, that's really where I want to go. And so I want to start with a puzzle. It's not really a puzzle, I give you the answer anyway. But these two things are actually very similar to each other, which is contradictory to what your brain is telling you as you look at the pictures. These are two barred galaxies, very famous actually in NGC numbers. And you can see here the bar in blue, the skeleton. I told you the blue part is mostly stars. You can see that. You can't see it here, it's hidden, but actually if I were only to show you the blue part, you will see something similar. So they have bars. The scaling that I used is about the same, considering that they have different masses. And the only difference really is the stellar mass, the total mass of the object. This is something like in log 9.5, and this is more like 10 point something. So they have a factor between 5 and 10 in mass. That's the only thing that makes them different. If you remember what I told you before, because this one is more massive, it's formed more stars per year. So the number of stars per year in this galaxy is higher. But of course, it's bigger, so it's easier for that galaxy to do this. But as a dynamicist, and also thinking about how we end up here, I want to understand what's going on. I mean, the skeleton, the gravitational potential that sets up everything is similar in this galaxy and in this galaxy. But if you look at the ISM, it's completely different. So maybe this one was, I don't know, perturbed by something coming by, or, I don't know. But I want to understand this. This is kind of my engineering background. When there's a box and it's closed, I want to open it and understand what's in there. So going back to the question I asked, what can we actually establish a reference pathway for those structures, the bars? and bar-driven evolution, how the bar will influence after it forms the disk itself. And I think this is key, understanding that those disks are the host of the star-forming regions, is the location where stars form all along since 13 gigayears. So if we don't understand that, that's a problem. Also because bars are, in the nearby universe, it's like 2/3 of all these galaxies are bars. Whether this is true at high redshift, it's not clear yet. You have a lot of papers showing that actually the number of bars in high redshift is maybe lower than that. But now they start looking with JWST, for example, and they see actually bars at z = 3 and 4. And the question is open. So that's what I would like to do. And now I come into the kind of description of what I think is wrong with what we have been doing for quite a number of years. So first, difficulties. So we want to understand how bars form, how they evolve, what's the impact on the disk, and how the disks evolve with that, the circular evolution. The problem is when you look at observations, of course, you look at a galaxy, it's a time-frozen snapshot. So you don't actually see the evolution itself, which means that if you look at a diagram like this, which is the strength of a bar with time, that's a typical curve from a bar formation evolution scenario. So it starts with the disk being a disk, and then it forms a bar, the strength goes up, and then it goes down again, and it goes up again on a long time scale, like 7, 8, 9 gigayears, if it survives, of course. And the problem is that if you are here and you observe this galaxy, you don't know if you're there, or there. You don't know if the bar is getting stronger. You don't know if it's weakening. You don't know at which stage you are, if it's the first phase or the second phase. And there is very little information for you to know that. I mean, there are ways, but actually this is a question I asked during my PhD many years ago to the experts. And today I still don't have the answer. I'm trying also to work on this, but I couldn't get an answer. And so which phases is it growing? Are we in? We don't know. Evolution is actually not monotonic. This is an ideal case scenario. The disk is formed somewhere, isolated, and goes on its life. It never happens like this. You can ask Anita about high redshift interactions, clumpy structures, and so on. It's a complete mess. So you will have this, but on top of that, you will have gas fueling, perturbation, interactions, and all this convolve with the star formation history and the feedback that coming from the stars, the star forming region, also from the AGN, if there is one. And basically, instead of looking at something like this, you may have, things which are much more complicated. And this is probably even simpler. So it makes the picture even more complicated. You have no clue where you are here. If you are an early bar, a late bar, if it's forming, if it's just dampening or not. And then on top of this, of course, the viewing angles makes it super difficult to know what you're looking at. Resolution, you go to high redshift, it starts to become a problem. And the other difficulty in observation is that actually a bar is not a bar. I mean, it's not like you have a bar, you can define, okay, it's let's say an ellipse with an axis ratio of 5, you're done. No, they're all very different from each other. They sometimes connect with spirals, sometimes not. Sometimes they have gas in the center, sometimes not. I mean, it's a mess. And actually, if you look, you can't see this picture, but the very nice work from Sophia Stuber in molecular gas, the cold gas that is tracing the orbital skeleton of bars appears like a beautiful set, like zoology. It's all different animals and species, and it's very hard to make sense out of this. The other thing, of course, is you have dust, and in the optical is a complete disaster because it blocks your view. And depending on the tracer you're looking at, like stars, molecular gas, old stars or new stars, you will see something different. The bar will appear different. So the other thing which is difficult is that all the metrics we have defined, and this is where I think we have done something wrong. So we defined a number of metrics to measure a bar, to characterize them, like just the size of a bar. So we have, for example, what we call the A2, is the second order coefficient of the Fourier decomposition of an image. And in principle, where it peaks, you have the bar, and you can define this is my radius, the radius of this bar. And that is super ill-defined. Depending if it connects with a spiral, then A2 will change. Depending if you look at 5,000 angstrom or 1 micron, it will change. It will change depending on the phase of the bar. It's a complete disaster. So this thing, and even measuring it, you give it to different people, they will find out with different number. So yeah, it's a complete dead end. So that's just for the size of this thing. But then if you want to look at the mass, the kinematic structure, and so on, all the metrics that we've defined, and we're so happy about, and there are thousands of papers trying to compare different samples, putting all this in diagrams, they are inhomogeneous and they are not robust. And this is, many more than 40 years of work. We still don't have good metrics to actually characterize these things, which is a bit amazing. Now, if I go to the second side of the coin, the simulations and the theory. So if you do idealized simulations where you have a disk isolated, you let it go, you form a bar, you put some gas or not with dark matter and so on, you have to consider so many parameters. I mean, the solution space is absolutely gigantic. Of course, the gas fraction will change how things go, whether your disk is extended or not from start. The concentration of mass in the center, if you put a black hole, a star cluster, maybe something in the middle, the geometry itself, how much dark matter and where it is distributed. Is there a bulge? And actually, I would claim spherical bulges don't exist. So if you do a simulation with a spherical bulge, it's wrong. It does not exist. So please don't do that. Actually, the bulges are 90% of the bulges we define are not bulges. They have nothing to do with what we think is something that bulge out of the disk. So we have to be very careful with this. Internal derivatives, if you change, your idealized simulation, it will completely change the evolution on a few hundred million years, but also on gigayear scale, time scale. And the other thing that you need to consider, and it's true for almost for any simulation, but this is even more critical here, the initial condition you're setting up when you set up a disk in a simulation, that is never realized in the universe. It's not like a disk starts, it's there, it has been formed like this, and then you launch it and let go. No, that's happening in a computer, but the universe that never does this. I mean, look at high redshift disks as they form. It's as messy as it can be. It's not something that is formed and then you get it started. And it's important to remember, these are experiments that will give you emergent properties that you could study, but these are not realized objects. Now, the other problem I have is that I've been, for example, teaching dynamics to graduate and postgraduate, and telling them about bars and the beautiful skeleton of how they form and all this. And I can tell you that half of my classes that I looked at back are wrong, plain physically wrong. So things which are in textbooks are wrong. And one of the example I want to give here is these famous inner Lindblad resonances. When you have a bar which rotates at a certain tumbling speed, this defines a frequency of rotation. But there is also a frequency which is just the frequency at which stars go around at the center of the galaxy. So you have two frequencies, resonances coming. And we learned that at certain resonances, one of them called the inner Lindblad, something happens and you have rings forming. And so now when you look at a galaxy, you see a ring and you think this is the right resonance, then you can basically calculate the speed of the bar just by very simple mathematics. But actually, someone like Mathias Ormani showed that the ring doesn't form at the inner Lindblad resonance. It's just was plain wrong. I mean, I learned that and I taught that, and this is wrong. It's actually defined a region, but actually the ring and the disk, they form at much smaller location, at much smaller radii, and it depends on the sound wave, it depends on the physics of your ISM, and forget it. It's so even things that we thought were really robust, they are wrong. And so we really have to go back and think about how we form bars, how they evolve, and what they do. Okay, another problem with simulations. Now idealized simulations are nice because you can put a lot of resolution and all the recipes you want because you have the computer power. And you do now cosmological simulations because you want the environment to be right. You start from the, let's say, Big Bang or a bit after, and then you launch it and you have this beautiful, very complex setup. The problem is, of course, then you have to restrict the recipes and the resolution and many other things, because it's just computer power that is eaten by all this. And the question I have, which is a very simple one, are the bars that we see in those simulations, even the best ones today, the ones that we see in the universe? I'm not saying this, should be exactly one-to-one, but are they roughly okay? My answer to this, I don't know if there are anybody working in this, it's no. They're actually, every time I look at a paper where they show the bars in the simulations, they look terribly wrong. They have nothing to do with bar. Oh, yeah, okay, they are elongated structure in disks, but that's all they have in common. There is, the entire spiral connection with the bar is not there. The actual structure of the bar is wrong. The Einstein distributed around is wrong. What does it mean? If bar and disks are so important and they form really quickly in a disk, it means that the evolution, so we have the endpoint right. The galaxy population, I mean, these simulations are usually calibrated with the z=0 population. But the entire disk evolution is wrong. And so actually, if you go back to z=1 or z=2, what you will see in those simulations is way out. Is that a problem? I can't answer. I don't know. Maybe we are lucky enough that it doesn't matter, that the evolution is fine, and then, overall, globally, the properties are okay. But I'll show you that there are some critical things happening due to the bars. And if we don't have that right, we may have the full entire evolution wrong. Whether this means those simulations are useless, of course not. They are, people have put a lot of efforts, and they're putting an incredible amount of thinking and tuning, and you have emergent properties that are important. You can follow almost any property of your simulation in time, but it's just if you think of properties connected with disks, SIG disks, we are far from that. Even the TNG50, which is used everywhere, has a resolution of about 200 or 300 parsecs for the stars. This does not even resolve the disks. The disks have a scale height of 100 parsecs. So you don't even resolve that. So how can you resolve the cold dynamics over gigayears of time? You cannot. And the other thing is, what are the right metrics? When you compare simulation and observations, how can you compare them together? I told you the metrics on the observations are not robust. And in order to connect this to observations, you need also to mod them, to use the right recipes and so on. It's very complicated. How you connect these two? It's just saying, oh, it looks like a bar. And this is the thing that we did, 10, 15 years ago. The simulators who have spent years and years of incredible efforts putting these simulations in, finally, they got disks that look like a bit like this, with spirals and so on. I can tell you they look stupid to me. They don't look like real disks. But in conferences, you had people saying, look, I formed disks now. And the question I would ask is, do you have a metric that you can show me that actually is relevant for the physics that connects with the observations? And the answer, I think, was no. Today, it's a bit better. And I think for the bars, we're still a long way. So we need to work together to find what are the right metrics, what are the criteria we wish to use in order to do this properly. Okay, then I'll try to go a bit faster because I want to show you actual results from simulations that I think are interesting. So the thing I would say is we do not have yet a robust picture, and we need to work on this. The literature is vastly inconsistent. For example, if you look at just a single thing, how much time it takes for a bar to form, given this number of parameters, you'll find everything. You'll find that gas delays the formation of a bar. And in another paper, you'll find that gas makes it faster. So what they do in medicine, they do meta-analysis of papers. And this is exactly what we should do. I think the amount of work that has been done is already there. We don't have to redo it, but we need someone to look back and say, okay, this study is great. It's very robust. I can take some of those, then this other paper, and so on, and take all the accumulated knowledge that we have and make some kind of meta-analysis and some conclusions, what we understand and what we don't understand. So that's what I want to say here. we need to specify what we know, and that could apply to any topic, what we don't know, and what we need, where we need to work on. Instead of trying to say, every time I have something, look, this is the result, I'm done, which is exactly what we're doing since, just because we want to, we're human, we want to promote our work, and we have spent 10, 15 years trying to get somewhere. So what we know, it's a list, probably non-exhaustive, about bars and disk evolution. I'm not going to go through, I don't have time. One thing is that we seem to see a lot of stellar mass-driven trends. Bigger galaxies do this, small galaxies do that. But are those actually mass-dependent, so driven by mass, or are those just secondary effects? Because bigger, certain environments give bigger galaxies, give bigger this kind of structure. So that's a question I don't know how to answer. What we do not know for sure is what is the subvolume of the full solution space that the real bars in our universe occupy. The volumes, the space of, the full solution space for all these bars, if I do a simulation, is enormous. And the real bars only realize a very small sample of that. And I don't know how to define that volume and why it is. I think we could learn a lot from that. Timescales, all these processes have different timescales, and I think we still don't fully understand how it goes. And how those events that I mentioned, when you go from idealized to cosmological, how does it change? You have let's say, a reference pathway for about to evolve. When you disrupt it by accretion, by whatever, how does it work? And finally, what are the metrics? We need to work together to define those metrics. Okay, what we may need to work on is, again, establish the metrics. But more importantly, I think bars are important because they're always there in the disk. It's very hard to avoid a bar forming in a disk. If we don't do this right, then we have a problem. Okay, let's go to hydrodynamical simulations and see if we can actually learn something from that. And we learned a lot already in the past. I'm not, putting everything in the garbage can. I'm just saying we have to be very careful about what we think we know, because actually we don't know all the things that we said in papers. So this is deriving from a project that I'm involved in, looking at local galaxies and resolved local galaxies at a scale of something like between 10 and 100 parsec to understand what we call the baryon life cycle. So the baryon life cycle is basically just saying you have a cloud, let's say a molecular cloud. It will form stars. It will disrupt its burst cloud. And then, a lot of things will happen. Supernovae will explode and so on. There will be feedback. And then you have a recycling of this. H1 will again produce molecular gas, and it goes on. And depending on where you are, the characteristic processes are emitting in different bands. It can go from ALMA to the near-infrared to the optical. And sometimes you need spectroscopy with instruments like MUSE on the VLT. So we basically try to cover this and try to reconnect all these different processes using the different traces that we have. But also, next to those big, large programs that we have, we also have simulations. And one of the example of one effort that was associated with this was done by Pierre Emsellem and these PhD students I mentioned, who basically looked at the Kennicutt-Schmidt and said, okay, I'm going to sample that set of parameters with idealized simulations, and I will just go with about 50 high-resolution simulations using Ramses. And so I would set up the initial conditions to resample the PHANGS, this project, the PHANGS galaxies. Resample means, I'll start with a disk, so they certainly not resemble PHANGS galaxies as they are today. So I artificially set up a pure disk and then I let it go. And so you have to do it right, because otherwise it goes in the wrong way. And how do you do this? Well, you use, there are many methods. The method we use is called MGE for multi-Gaussian expansion. And this is just a representation of one galaxy here, which is an early type, and here the Sombrero galaxy, if you know it, and the model that we can do, using that technique. And so we're not going to do this with the PHANGS galaxies, but we're going to use the same formalism to set up the initial conditions. So meaning stars, dark matter, and gas. to start and, for example, I get these kind of simulations at the end. So the first thing that we learn is, you launch a disk and it takes some time to form a bar. How does it work? Is the diagram that I showed you, the bar strength at the beginning is basically 0. This is the famous A2 parameter, by the way, not robust, but let's use it for the moment. Then the bar forms. It takes, depending between 100 million years and a couple of giga years, depending on the initial conditions you put. You can delay it forever if you want. And then at some point, something happens here, it damps a bit, and then it grows much more slowly with time. So these are the 2 phases, basically. But actually, Eric found that it's a much more complicated picture. As you go from low mass galaxies to high mass galaxies, remember the low mass galaxies, they form fewer stars per year, but they actually have much higher gas fraction. They have much more gas. And so it's very, very different. And just look at the bar strengths here. You see these oscillations. You see the first phase. But actually, we found out that there are 4 phases. There's the first, start trigger of bar formation. Then something happens in the middle. So as soon as the bar starts forming, then the gas starts to get inwards and form a reservoir of gas in the center, in the central, let's say, few hundred parsecs. Then there is a starburst, that's phase C. And after this post-starburst, there is a long-term depletion of gas due to just the bar working on what is there still as an ISM. And so you can think of 2 phases or more complicated 4 phases. This is already something that we learned from those simulations. Whether this is right or not, we need to check. That's important. So this is how it looks in one of those simulations. You have, the gas density, the molecular gas, temperature, the old stars, and the newly formed stars. And you do this for a few giga years, and you end up, for example, with a galaxy that looks like NGC 1365, sorry. And this is, for example, the stellar velocity field that we measure with MUSE, and this is what we get after 7 giga years of evolution in this particular case. And I'm not going to go back because this is not the subject of my talk, but it's just to say we get things that look very much, interesting. These are not true things that not realized. The computer simulation has nothing to do with reality, but the question is, can we learn something from that? And one thing that we can learn, for example, in this particular galaxy, there is a beautiful ring. There's a huge bar, which is 10 kiloparsec wide. So you see only this kiloparsec size ring. And if you look at the molecular gas, it follows really well these ridges of gas coming in. And in the simulation, we see the same. This is the same scale, exactly. And there is a little thing here. And actually, if you look at the data, you can also see that there is something in the middle that is weird. It's a bit of a disk of gas. And the weird thing is that it doesn't form stars in the center. The shear there is too high. And this is exactly what we see in the simulation, in the observations. And this is typical of the gas flow in a bar. Now, what we learned from this is now we have the simulation. So we can look at how it changes with time. And actually, what we found out is that the changes, the speed at which the structure changes is super quick. In less than 20 mega years, everything changes. So the illusion that we have this structure and it will stay forever, or at least for hundreds and hundreds of million years, is wrong. Things are changing very quickly. The clusters are coming in. The gas is disrupted by feedback. So what stays is the skeleton, but everything else changes very rapidly. So now let me go to the main result I want to. How much time do I have? Yeah. So just to show you how we can use some of those simulations, a reminder is we have about 50 probing from low mass to high mass with all the different varying conditions in the PHANGS sample. And we go back to a paper by Amelia Fraser-McAlvey in 2020, where she did something really nice with Manga. Basically here, it's a survey of galaxies, of low redshift galaxies, 10,000 objects. And she looked at where the H alpha, which traces the star-forming regions, is. And she found out that in the low mass galaxy, the H alpha is elongated within the bar. So you have a bar, and the gas is basically emitting along the bar. But now if you go to higher masses, it's in either at the end of the bar or in a central starburst or in a ring. And you can see the coloring of these categories. It really is, it looks like there's a big change, an abrupt change from high mass to low mass, which, you know, is puzzling. For dynamicists, it's like, what? Why is there this change? And it means that here stars are forming within the bar. So accumulating along the bar, here it's just in the middle. So it will change the entire evolution of the disk. Okay, so what do we see in our simulation? This is a low mass, this is a high mass. And just to tell you, these two simulations are exactly the same. The only thing we did was to multiply the mass by a factor of 3 for everything, for the gas, for the stars, for the dark matter, and so on. That's all. And you can see the evolution after 5 times the formation time of the bar. This is messy, this is structured. This is exactly what Amelia has seen in the observations. Interesting. So, I mean, this is probably complete rubbish because we have so many things that don't work in the simulations. The resolution is not very good. It's 10 parsec. It's really good, but it's not fantastic. But if we do reproduce this, then we can look at it and see why it's happening. And actually, if you look at the new stars, you see the same. The new stars are in the center. Here they are along the bar, all very messy. So this is very structured. This is completely chaotic. Now the game is, where is the center of these two galaxies? Looking at the ISM. I just took those 4 thumbnails of the gas density structure, and you have to tell me in this galaxy where is the center. And everybody says, yeah, it's here. Yes, you're right. Where is it here? I can tell you, you're going to be wrong, whatever you say. There is no center in the gas density. So the bar forms, but the ISM doesn't tell you where the bar is. It's hidden. Same here. What is the time sequence of those 3 things? I mean, here is very clear. You start here, then you grow, and then you grow. Here, I don't know. Actually, it's there. Okay, it's the same. It's completely crazy, chaotic. And the only difference between these two is a factor of 3. That's all. That's all we did. Okay, so we see the same here in the molecular gas. You can't make which one is which. Here you really see an ordered evolution. And it's the same with the disks. For example, here you see the disk which is forming in the stars, a very nice exponential disk due to the star formation in the massive galaxy. In the low mass galaxy, nothing is happening. And you could see this in also the high mass are the red, the low mass are the blue. You can see that in the gas density, all the gas density changes from there in the low mass to there. So there's a depression of gas within the bar. This is just one scale of the bar, one bar scale, sorry. And you can see there is a difference. Now the problem is, what is the difference? So if you look at the low mass versus the high mass, this is the probability distribution function. So basically the number of clumps that have a certain mass. And you see a very nice log normal. And if you look at the evolution, it doesn't really change before and after the bar forms, which tells you that when the bar forms, it's a very strong change in the potential, but nothing happens for the gas. It doesn't care. It just goes on and forms stars as it did before. You cannot tell there is a bar, even though it's there. While here, clearly, the changes are enormous. You start creating structure, high density peaks, low density peaks, and so on. So let me tell you why now. So in principle, this is explaining, but it's a bit too complicated and I don't have time. But as you go from low mass to high mass, what happens is that basically here, the time scale to form this structure in the gas is very, very long. Actually, at these masses, it takes more than 15 gigayears. At the high mass, it's almost, it's super quick. And if you look at the intermediate case where you have just a mass in the middle, it's actually the intermediate case between this and that. It starts forming, but it's a bit slower than this. And the reason I'm going to try to explain with this diagram. When the bar forms, let's say this is the bar, what happens is the skeleton, the orbital skeleton is fixed. This is the gravitational potential. The stars are dominating the potential. And it forms this flow of gas. So the gas is flowing from here to here and from here to here. This is, of course, super simplified. But this is a 1D structure. If you have two 1D structures that goes against each other, basically it defines a center, a central region. So the center is defined by this flow. If you have a center, then stochastically you will form stars here a bit more than elsewhere. And maybe at some point, this will be central enough that the stars you form, which will stay there, form a mass, a concentration in the center, which makes this even stronger. So the flow will then even be more structured because there is a center now, and it can go on. The problem is that imagine you disrupt this flow a bit. If you disrupt it a bit by feedback, doesn't matter, it goes on. Now you disturb it a bit more, it starts to get really crazy. And then if you disturb it really a lot by pushing a lot in all directions, then you get a mess and you can't form, there's no center anymore. There's no attractor in the center. So you will never, the probability to form something that will define the center is basically zero. And it will take forever to actually form a central mass concentration. And that's exactly what happens. Imagine the potential, the only thing we change is the potential. If you, since the local feedback is always the same, the supernova is 10 to the 51 ergs per, that's it. So locally, you will have always the same velocities in pulse. But the background force is either very high or very small. And when this perturbation becomes too high, then it dominates and then it's a mess and you never form it. And that's exactly what happens. And if you look at the evolution between the low mass as you go to the high mass, is exactly this. It's a mess, it's a mess, it's a mess, it's a mess, it's a mess. And then suddenly you start seeing these structured center, rings, spirals, flows, and so on. This is exactly what you see here, just in color, different bands. These are barred galaxies. I can tell you there are bars. Here, there's a bar. Well, you can't see it, it's hidden. Here, just looking at this, you know there is a bar. It's clear. You don't see the stars, you just see the ISM or the dust. This is superstructure, and this is exactly the reason that we put forward. And so it's a different view from Justus Neumann in a paper that is going to be submitted. You see the mass ordered set of JWST images, which is showing the PAH, and you see exactly the same. It's complete mess and very superstructured. And the beauty of this is that because it's structured, the ISM is structured, it forms a central mass concentration, which is actually not a bulge. Don't say it's a bulge, it's a disk. And you can see it in what we call the V over sigma, so the amount of ordered rotation versus dispersion. You can see these structures here using spectroscopy with MUSE. You can do these maps, and you can see they are all over the place. And here they are not. It's just straight. There is no central structure. Mm-hmm. It's exactly the same. Mm-hmm. Okay, so take-home messages to close up. So if you form a disk, it's almost impossible not to form a bar. I mean, I can do it, but it's hard. I mean, of course, if you put a lot of interactions, or unfortunately, interaction also trigger bars, which are slightly different. You can mess things up, but it's really hard to avoid. So if you have disks, you have bars. It's almost unavoidable. In the high mass galaxies, there are key agents of disk evolution. Because of those flows that are structured, it will form central mass concentration. It will redistribute the gas and the stars at a very, very fast. And so it will create all this structure. In the low mass galaxies, the bars are hiding. You can't see them. And this is why it's very hard in a low mass galaxy sample to know how many bars there are. So there are these, what we call the galactic speed easies, and I can tell you later why we call them like this. So the star formation regime, the PDF, everything is like there is no bar. Actually, the galaxy doesn't care that there is a bar, which is very funny, strange. And this is, in our view, just feedback driven. So those imprint of gravity and feedback, the fact that it changes, it's a continuous change. It's not just, you're on one side or the other, but that continuous change is really abrupt. And it goes from a 1D flow to a 3D mess. And that's why we think it's happening. What about higher redshift galaxies? They have much more interaction. They have up to 70% of gas. So it would be interesting to understand how it works there. The problem is, as long as you have no bars in those simulations at redshift, you're probably not doing anything right in that context. And so there will be a differential evolution between the real universe and your simulations. So you need to address this. And I think I want to put a positive note. There has been a huge amount of work, including in the cosmological simulation side. So we don't necessarily have to redo everything saying, oh yeah, this was all wrong. No, that's not what I'm saying. But I think we need to go back and really look at what we learned. And what are the things that are robust and what are the things that are not robust? If you go to medicine, it's the same. If you think about a treatment that is absolutely not efficient, you will find a paper that says it's efficient. But that paper is a minority of papers. That kind of result is a minority. If you do meta-analysis, you will find out that maybe that study was not very robust, the sampling was not right, and the protocol was a bit sketchy and so on. So you can put some values to these things. And when you take a step back, you see, actually, I have robust demonstration that this is efficient, and this is how it works. For some reason, we don't do this in astronomy. We just publish and we forget. We publish and we forget. And we reference the papers that will just reinforce our results, which is exactly against science. And so we need to take a bit of a few minutes just to think about that. Thank you very much.